continuing on with our gas laws notes, we get to one of the most important, there's two really important gas laws, and this is one of them. It's called the combined gas laws, and that's because it comes from multiple laws that have some relation to this, but it's with something being held constant. And so that's one thing that we often have, is that one variable is often being held constant, and then we're able to solve for the unknown. And all the other variables would be given. So again, based off of our last notes, P stands for pressure, V stands for volume, T stands for temperature, and if you remember, temperature must be measured in kelvins when we're dealing with gas laws. 1 stands for the initial conditions, or what's at the beginning, and 2 stands for the final conditions, or what we have at the end. And again, generally something's going to be held constant, and if it's held constant, we just ignore it. So if the pressure was held constant, we would get rid of them. We'd have V1 over T1 is equal to V2 over T2. And we'd be given 3 numbers, and then all we'd have to do is solve for the last one, the fourth one. Sometimes you will have problems where you're given all things that are changing in some way, and then you're asked to solve for one of them. For instance, T2 would be what we're solving for. We'd have P2, V2, P1, V1, and T1 all given to us. We would just have to rearrange the equation to get the correct answer. So here's our first problem. The pressure of a 2.50 liter of anesthetic gas is changed from 760 millimeters of mercury to 304 millimeters of mercury. Millimeters of mercury is just a unit for pressure, and liters, as you remember, is a unit for volume. And we said at the beginning of our notes in the last video was that liters is the same as decimeters cubed. So if the temperature is constant, what is the new volume in decimeters cubed? Well, that means whatever my final number is, it's going to be the same, because 1 liter is equal to 1 decimeters cubed. So that's probably our easiest conversion that we would ever need to make. Okay, and it said that temperature is held constant. So again, I'm going to say temperature, I'm going to get rid of them. My new equation looks like this. P1 multiplied by V1 is equal to P2 times V2. And I'm going to be looking for V2. So that means to rearrange this equation, right now I've got multiplication between the P2 and the V2. I want V2 alone, so to undo multiplication I have to divide both sides by P2 to get V2 on its own. And I always want to write out my givens. This is a key step. It'll make sure that you don't get anything flipped around, you put in the wrong pressure in the wrong place or something like that. If you've got it all listed out, you're going to be at an advantage compared to those who just try to plug it in right away. So I've got 2.50 liters, 760 millimeters of mercury, 304 millimeters of mercury. Since these pressures have the same unit, I don't have to worry about making any conversions there. And again, liters and decimeters cubed will be the same answer. So I rearrange my equation. Maybe, there we go. And I get P1 times V1 divided by P2 is equal to V2. And then I just plug in my numbers. So 760 millimeters of mercury is my P1, multiplied by my V1, which is 2.50 liters. And I divide that answer, and I put it in parentheses because I want to get that answer first, and then divide by 304 millimeters of mercury. And the reason I do that is just because I don't want my computer or calculator to try to put things in a different order. Sometimes when they put it in a different order, you end up getting the wrong answer. And when I type all of that in, my millimeters of mercury units cancel out. I'm left with liters, which is the same as decimeters cubed, and the answer is B, 6.25. My next problem is assuming that I have a constant pressure, so my P is going to be canceled out this time. And it's the contents of a 100 milliliter balloon at 38.0 degrees Celsius is heated to 54 degrees Celsius, and I want to know the new volume in decimeters cubed. So my P's cancel out, my givens are there, and I notice right off the bat 2 bad things. 1, my Celsius should be in kelvins. Always have to have kelvins as my temperature unit for temperature. So I'm going to have to make that conversion, which just means I add 273 to each of those T1 and T2 values. And then also I see that I'm going from milliliters to decimeters cubed. Well, I know that there's 1,000 milliliters in a liter, and 1 milliliter is the same as 1 decimeters cubed, so that means there's 1,000 milliliters in a decimeter cubed. So if I have 100 milliliters, I really have 0.1, or 100 divided by 1,000, 0.1 decimeters cubed. So those are my final values after I've converted. And then I see my equation. Went in the wrong order here. I have V1 over T1 is V2 over T2. To get V2 on its own, I multiply both sides by T2. My T2s would cancel out on here, and I get this equation, V1 times T2 divided by T1 is equal to V2. I just plug in my numbers, and I'll get my answer, which I believe is D, 0.105. Now here's my second big equation. So I had the combined gas law. Now this is my ideal gas law. And it's a combination of a whole bunch of different guys' laws, Avogadro with the combined gas law, and it's dealing with moles, which brings us back to what we started out the first set of this notes with. And our equation is PV is equal to nRT. In other words, pressure times volume is equal to moles times a constant times temperature. And the big question is, what does R, that constant, stand for? It's called the universal gas constant. And with the unit of liters, atmospheres over Kelvin moles, my value is 0.0821. Now that universal gas constant will change depending upon what units you are dealing with. And we'll see that on the next slide. And again, notice that if I'm using this ideal gas constant, pressure has to be in atmospheres, the volume has to be in liters, and has to be moles. So if you see grams, you have to convert it. And T must be, or temperature must be in kelvins. So again, this is in the data booklet, so it's not something that you're going to have to memorize. And in this gas constant, the R value is giving us a different unit. Since it's giving us a different unit, it's joules over Kelvin moles, the value is different. So it's not 0.0821 anymore, it's 8.31. So be careful which equation you're using and what R value you use so that you're using the correct unit. And the equation's given to you too in your data booklet, so you don't have to memorize that equation either. So let's put this one into practice. We have, we're wondering how many moles are in a 3-liter sample of methane, which is CH4, at 300 kelvins and 1.50 atmospheres. So I'm using that equation, PV is nRT, because that's the only one that gave me moles with liters, temperature, and pressure in it. My givens are 1.50 atmospheres, volume 3 liters. I'm looking for moles. The R that I'm going to use here is the 0.0821 liters atmospheres over Kelvin moles because I'm given liters, kelvins, atmospheres, and I'm looking for moles. And I have a temperature of 300 Kelvin. Since I'm looking for moles, I need to undo this multiplication that I have. I have N multiplied by R multiplied by T. I want N by itself, so I'm going to divide both sides by R times T. So PV divided by RT is equal to N. And so I put it all in. So my PV, I'm going to multiply first 1.50 atmospheres times 3 liters divided by my universal gas constant 0.0821 liters atmospheres over Kelvin moles times 300 kelvins. And I should get my answer. Sorry, I thought I'd be able to cancel out units. I have liters on the top of a fraction and liters on the bottom of a fraction. That means they're going to cancel out. I have atmospheres on the top of a fraction and atmospheres on the bottom of a fraction, so those will cancel out. I have kelvins on the top of a fraction and kelvins on the bottom of a fraction, so those will cancel out. And then I'm left with moles, which is really 1 divided by 1 divided by moles. So if you think back to your math rules, if you have 1 over a fraction, it flips the fraction around. So if you don't believe me, take 1 divided by a half. or 1 divided by 0.5? You get 2. 1 divided by 1/2 is 2. So in that same way, 1 divided by 1 over moles is just moles, which is the unit that I want.